In this video, I'm jumping back to the serial position curve for a second because there's two aspects that make that curve very interesting. And I already briefly mentioned them, but I just want you to have some understanding of why these two parts of the curve have been linked to different memory systems. So here's the serial position curve again. And as you see again, right, the first couple of words are better remembered. The last couple of words are better remembered. And the ones in the middle are typically not remembered as well. The first couple of words have been linked to long-term memory, and the idea is that if you're being read those words first, you have some time to repeat those words a couple of times as new words are coming in, but because of that repetition, some of those words would actually make it to long-term memory. So that's the notion behind what's called the primacy effect. Primacy meaning the first couple of words. The primacy effect reflects long-term memory. On the other hand, the last couple of words are very recent, so the recency effect there that you see suggests that those words are still in short-term memory. Now, of course, talk is cheap. Is there an actual way to test this? Well, it turns out it's pretty easy to do so. So, first of all, what we can do is again a task where we read out the list of words, but before people get to recall them, we actually have them do some other task for a little bit of time. And we already saw that if you have people do something else for just the tiniest bit of time, so for example, counting backwards for just 10 seconds or 30 seconds, very quickly short-term memory gets wiped out. So if the recency effect is due to short-term memory, then it should be that if we wipe out short-term memory, we get rid of the recency effect. And what you see in this graph is if you have three different conditions, one where there's no counting backwards, people are just given the words and they recall them. In that case, you get the recency effect. Have them count backwards for 10 seconds, it's greatly reduced. Have them count backwards for 30 seconds, it's completely gone. And interestingly enough, these manipulations have no impact on the primacy effect. And again, supposedly because those words are in long-term memory. Is there a way to selectively wipe out long-term memory? Yes, there is. So if you think about it, if you present the word list either slower or faster, if you present it slower, it would give people more time to repeat the words, making it more likely that they would make it to long-term memory. If you read the word list faster, the words would have less time to make it to long-term memory. And indeed, based on that manipulation, you see that yes, for slow reading, you get the recency effect. If you read off the words list very quickly, the primacy effect gets wiped out if you read the words very quickly because people are not able to actually repeat them, and as a result, they don't make it into long-term memory. So all of this gives some good evidence that short-term memory is a separate type of memory that's separate from long-term memory. And in the original model, it's called the Atkinson and Schiffer model, by the way, but it's just the idea of three different stores, the sensory registers, the short-term memory store, and the long-term memory store. You basically see all this boxology, and you can link the short-term memory box and the long-term memory box, again, to different parts of this serial position curve. So long-term memory explains the primacy effect, short-term memory explains the recency effect. Now, nonetheless, there have been some trouble or difficulties with this model, and in the case of the test that we're just talking about, here are some of the difficulties. For example, first of all, there are patients who actually have long-term memory impairments without having short-term memory impairments, and there are also patients who have short-term memory impairments without having long-term memory impairments. And especially that second case is problematic. Why is that? Well, if you see in this diagram, long-term memory actually gets accessed by short-term memory, and then short-term memory is involved in actually responding. So, if you're being asked a question like, in which state do you live? Short-term memory would activate long-term memory to select New Jersey or Pennsylvania, depending on where you live. Long-term memory then that information gets transferred to short-term memory, and then you respond based on your short-term memory. If that's the case, if this part here is damaged, it should be the case that it looks like you have long-term memory damage as well. In reality, there are actually patients who have damage to short-term memory but not to long-term memory. So that's an issue in this model. Second, if you look at how quickly people forget, it actually turns out that it's not just the amount of time that people are doing something else, but it's more related to the difficulty of the task they're doing in between. What I mean by this is that, for example, if you have to, say, remember 5 letters and you need to count backwards by 3s for 5 seconds, that would actually be worse for your memory than counting backwards by 1s for 10 seconds, because counting back by 1 is easier, right? So I'd say 10, you go 9, 8, 7, 6, 5, 4. That's very easy. If I say 10 and I count by 3s, 10, 7, 4, 1, that's a harder task. It turns out that difficulty rather than time is more predictive of how much the short-term memory store gets wiped out. And then the last point, how much interference there is from the material that you're working with in the second task actually depends on how similar that is to the first task that you're supposed to be doing. So let's say I give you 3 words to remember, and then in one condition I tell you, listen to the headphones, and in 15 seconds, if you hear a tone, tell me that you hear the tone, and then after the 15 seconds I ask you, tell me the 3 words. In that case, people can do this task very easily. However, in the other case, I tell you 3 remembered words, and then for 15 seconds you have to actually need to monitor whether you hear any syllable that shows up in one of the remembered words. Surprisingly enough, because there's so much overlap between these 2 tasks, you actually end up wiping out short-term memory and people don't remember the words as well. So these findings present some challenges for this standard box model. And then the last issue with this model too is that short-term memory might not just be some sort of static box. It may be that, first of all, depending on what kind of information we're talking about, it gets activated at different points in time. So for example, right now, you're listening to me, you hear my voice, so there's auditory information. You're processing what I'm saying, so there is what is called semantic information. And then, if this were a normal classroom, you could also see me, so you would also get visual information. And in fact, you're getting visual information from the slides you're looking at right here too. Maybe these different kinds of information form different kinds of codes that all become kind of active at different points in time. And maybe that's a more useful way to think about the way in which memory is working and operating. So we'll talk more about codes in the next video.